All right, shall we get into this? If you did the mini exam and you want to turn it in for a grade, please set it up here for me. Stapler's up here if you need one. Remember what I said last time, the mini exam that's due a week from today is, I think, a little more straightforward than the ones that you've had in the past. I don't know, you'll let me know, I guess, how it goes. All right. Well, we have our first exam 2 weeks from today. Our first exam. So I was thinking about how we're going to do that exam. And I came up with two ideas. And I was going to have you as a class vote, and then ultimately I'll just make the decision. But I want to kind of see what you all feel. So here are the ideas I have. First idea is that you come in to take the test 2 weeks from today, and I don't really give you any sort of prompt as to what to expect, but it's completely open note, open book test. Like, you can use your notes, you can use your mini exams, you can use anything that you have, your homework, you can use anything you want, right? Well, you can't just go and like Symbol Lab and all that, Wolfram Alpha, all that, right? But you can use all your resources, right? The other is where I give you a more direct, like, here's the types of problems you're going to see, but I don't let you use your notes and your book and everything else. I maybe allow you to do like a reference sheet, like maybe one page where you can write some stuff down, you know? And then, of course, all the formulas that are online in Canvas, you can have those as well. But I mean, just that's my initial thought. What do y'all think? Anything?
Option two.
You like two?
The open book would be nice, but if I don't know exactly what we're going to be looking at, I won't be flipping through an entire notebook for notes.
Okay.
Around.
So you're feeling more of like, give you some direction, but it won't be open note. Any other opinions? We don't have to decide right now, but you like open note?
That's just how I have been approaching the quizzes as well.
Yeah.
Just going.
So we got one for one way and one for another. So
How many problems does that have?
I don't know. I have to make it where you can finish it in 100 minutes, right? So that's always tricky. Yeah, I don't know how many problems there will be. Think about it. Think about it. Okay. All right. So maybe we'll revisit that Monday. If you do decide, or if we decide that it's going to be just more of like a real test where you don't have open notes and stuff, next week I will give you some sort of guidance. That way you'll have the next weekend to like get things in order and kind of study and get ready. All right? Okay. Turning it? Yep, right here. Thank you. All right, well, what were we doing last time? Yeah, question, yeah.
I was on your old lectures on YouTube.
Yes.
You're saying that if you fail the exam with 50%, what was going to drop off the student?
Yeah, so I used to have a policy in this class where you had to score higher than 50% on the midterm and the final. Like if you get lower than a 50 on the final or midterm, you don't pass the class. But that's an old policy. That's not our policy. Yeah. I don't remember the weight of the mini exams, but I believe if you do well on the mini exams and don't do well on the midterm and final, you can still, get through the class. But
I think the mini exams are like 50%.
yeah. So I don't know. I'm going to share something with y'all. I was thinking maybe I wouldn't share this, but let me share this with y'all. So I may have mentioned this at the beginning of this class, first day or something. So this is an email from one of my students from the last time I taught Cal 3, which was spring. And trust me, this is not the way every student felt, okay? But I just want to read it to you. So it says, hello, I wanted to thank you for a great semester. Walking into this class, I did not know what to expect, especially when you had us watch a lecture before the class even started, because I actually had them watch a lecture before. But I learned a lot from you, and I persevered to the finish. This class has definitely been my most challenging one so far, and I am grateful for it. I was pushed to the extent of my abilities and truly feel that I came out a better and smart person for that. I'm glad that you continuously pushed us and were there to help guide us through the course. I felt a sense of accomplishment being able to finish the calculus book and blah, blah, blah. So we can sit here and talk about grades and passing, and I know that's important, but really what I want you to walk out of this with is that you have gone to places that you hadn't, that you didn't think you would go, you know what I mean? Like to push yourself to a place that you raising your bar higher than you thought. You know, that's what I'm hoping for, in that you come out of this being a better student at the other side of it, you know? That's really what this is about, because I want all of you to go become whatever engineers and all that stuff. And, you know, I've got students that I've had for calculus that have gone on. There's one, I'm gonna have him try and come in here and talk, because he's doing his PhD, he's working at NASA. And so like, I'd like to have him come in here and talk about like what his experience was here, because he did the whole calculus sequence here. You know, I think he did IFEQ here. So, you know, just to show like, yes, you can get through this and go on and do whatever you want to do, but you have to do this, right? So anyways, yeah, this class is more than just like all this stuff. It's about you becoming more evolved, you know? So, okay, let's get back to this. So last class, the main takeaway from last class is we're still working with surfaces. We're going to some point on that surface. We're standing there and we're pointing in some direction and we're saying what is the derivative or what is the slope of the tangent line in that direction. And we ended class with the idea of, hey, if you are standing on a surface, just arbitrarily at some point, will it be easy to determine which direction you should point in so that you would have the steepest rate of ascent in that direction? And I think we said it seems like that would be hard, but it's actually turned out to be easy. So let's just pick up right there. So we have first the actual formula for the directional derivative. It says if you have your surface and you've got your direction vector, which has to be a unit vector, tells you which way to point, then the slope of the tangent line in that direction at that point on the curve would be this right here. Okay, and we did two examples, right? We did two examples of that. And now we're going to change the notation a little bit, and this is the big part to be able to answer that question, like, is it easy to find the direction? This is something that you wouldn't naturally do, but it's pretty simple if you look at it. It says if you look at this formula, right? If you look at this formula, then you can rewrite that formula like this. Okay, so what is this? This is the dot product of two vectors. The first vector is the partial of f with respect to x, evaluated xy. And then the second component of this vector is partial of f with respect to y at the point xy. Take that vector, dot it with AB, and remember dot product is very simple, right? You just do this times this plus this times this, and that is exactly what this formula is, right? So it's just realizing that that formula can be written as a dot product. It can, right? And if we do that, right, then this is a very nice condensed notation for that directional derivative. It's saying you take the vector that is made up, what are the components of this vector? It's just the partials, right, of the f function, the two partials, and you're dotting it with that direction vector, right? And that will give you the slope of the tangent line in that direction. All right. Because it can be written as that dot product, and because that vector that we create from the two partials is so important to us, we have a special name for it and a special notation for it. This vector made up of the two partials here is going to now be written this way, or we'll write it this way. And this symbol right here stands for the, what does it say? Gradient, okay? This means the gradient of the function f. So if somebody gives me a surface, right? Someone gives me a surface f. The gradient of that surface is a vector. And what it is just the vector made up of the two partials. That's it. Okay? That is called the gradient vector. So we have that the directional derivative, I'm just writing what was already up here. The directional derivative of f at xy, right, was a times partial of f at xy plus b times partial of f with respect to y at xy. That was the original formula given to us. Then what we're saying is that that is the same as taking the vector partial of f with respect to x, partial of f with respect to y, and dotting it with ab. That's just another way we could have written that. And that this, right now, is what we call the gradient of f, and we're dotting it with the vector ab. It's all just notation, right? It's all just, this means that, which means, and when you dot them, it means that. All right, so let's do an example here. This is just to make sure you understand the language. So I've given you what? What is that right there? A surface, right? Z equals f of xy. That is a surface. And I'm asking you to find the gradient vector of that surface. So all you need to do, right, to find the gradient is find this vector. It's the vector made up of the two partials. That's it, right? So let me do those partials on the side. Partial of f with respect to x. Let's go ahead and do that. Okay, this is a little bit complicated, not much. We have addition right here, right? So we can do the derivatives separately. The derivative of e to anything is itself, right? Times, now you have to take derivative of what's up here, the x times y, and you're holding what constant? Y, right? Because we're doing the partial with respect to x. So what is the derivative of xy with respect to x? Y. Just y, right? Because the derivative of x is 1 and y is the constant. So it should just be y here. Are we done with the e part? Yes, we're done with the e part. Okay, move on. Plus. All right, now we have cosine of something, right? The derivative cosine of something is negative sine. Why don't I make this a minus then? Minus sine of x plus y. And then times the derivative of what's in here. Be careful, x is our variable, y is a constant. So derivative of x would be 1 plus derivative of y would be 0. So this should just be 1 out here. So I don't really need that one, but there it is. Right? That's partial with respect to x. Partial with respect to y, very similar to what we just did, right? It's going to be e to the xy still, but now times x, still minus sine of x plus y, right? That's still the same. And then times 1 still, right? So there are your two partials. So if I slap those two partials into a vector, that's my gradient vector. So the gradient of this function is e to the x, y. I could put the y in front if I want. I'll just leave it. Comma. And then e to the x, y times x minus sine of x plus y. Vector, right? It's a vector. And what I know is that if somebody gives me a point on that surface, right, and somebody gives me a unit vector that gives me the direction, then if I plug the point, the x and y coordinate of that point into here and here, x and y of that point, and then they give me the direction vector, and I just use the a and b and dot the two, I'd get the slope. Right, but that's not asking for that, right? It just wants a gradient vector, we're done. All right. Now, everything I've given you so far in terms of the directional derivative was if we had a function of two variables, right? That's if we had a function of two variables. So if somebody gives you f of x, y, we're talking about a surface, and the directional derivative is us standing on that surface pointing in a direction. But what if somebody gives us a function of 3 variables, right? That means you plug in an x, a y, an x, a y, and a z. That point gets plugged into a function and then an output comes out. We can't see this anymore. This f here is no longer a surface in 3-dimensional space. It's actually like a surface almost in like 4-dimensional space. It's impossible for us to really visualize it, all right? You see that there's a big difference here? Okay. This says that even if you have a function of 3 variables, we can still define a directional derivative. The directional derivative is, as you might suspect, well, first you need a direction vector, but notice now this direction vector, which again has to be a unit vector, has to have 3 components. So you have to, back when the surface like this, I just needed to know which way to point like this, right? But with the function of 3 variables, I actually need to know which way to point. How can we visualize it? Okay. Imagine that you have, I'm trying to get you to see what this, one way we can look at this. Imagine you have this like 3-dimensional blob sitting in space, okay? This 3-dimensional blob sitting here, right? And at every point on that blob, let's say it's a solid, okay? Let's say this is solid. I take some point there. You'll agree that has an x, a y, and a z, right? That has a point. Now, let's say I have a function that takes that and returns to me some answer. Okay, so I don't know what it is, but it's going to return to me here, let's say some number. And let's say that that number is the temperature at that point. Okay, the temperature at that point in the solid. Then this can kind of start to make sense. Because if I say what's the directional derivative, what it is if I'm standing at that point in the solid, you give me a direction vector, so you tell me some way to point. You give me some direction to point in, u. The directional derivative will give you what then? What will it represent? It won't be the slope of tangent line anymore. What would it be? If you go from there, you start going in that direction, the directional derivative gives you the what? Rate of change in. What was this measuring again? The temperature, right? So it gives you the instantaneous rate of change in temperature. So as you move from here to there, you're actually going to see that little step in that direction is not going to be a slope. It's going to be how much the temperature is changing at that point. Understand? So it's a little harder to visualize this because the 4th dimension here is actually the temperature. But we can still try and understand it. Okay. At the end of the day, the mathematics of it is this. You have a function of 3 variables, a unit vector, u is the vector ABC. Then the directional derivative is exactly what you would suspect. A times the partial of f with respect to x plus b times the partial of f with respect to y plus c times the partial of f with respect to z. Again, we can rewrite this as a dot product, and therefore the gradient of this f would be the vector with 3 components where it would have the 3 partials, right? With respect to x, y, and z respectively. Do you think this extends to 4 dimensions? Like if you have a function of 4 variables? Yes, 5, 6, 7. So this extends. We're going to stop here. We won't go past this, but it does generalize. All right, so here's just so we can make sure we understand how to do the computations here. Ooh, what did I do? No, I don't want sticky keys. I meant to hit enter, not shift. All right, so there we go. We have a function of 3 variables. It's x over y plus z. And the first thing is to find the gradient vector. Can you all see that function okay? X over y plus z? All right, so let's find part A. Let's find the gradient of f, which should be the vector made up of the partials, the 3 partials. And so let's start with the first one. Partial of f with respect to x. What is it? This might help. Can we rewrite the original function like this? Yeah, we can rewrite it like that, right? And then if we're differentiating with respect to x, this is our variable and this is what? A constant. Okay, hold the constant. What's the derivative of x? 1. So that should just be our answer, right? So that should be 1 over y plus z. I hope that makes sense. Now, if we want to do the partial of f with respect to y, that's going to be a little different, right? So here's the way I would look at this. I would say I could rewrite the original. This is my original function, right? I'm just going to call it f. Is that all right? See, this time the variable is inside this thing, right, which was down the denominator. So if I take derivative here, I have to do some chain rule, don't I? And I don't have to do product rule because that's a constant, right? This and this are, this and this are constants, aren't they? So when I take this derivative, the x will come for the ride, right, times. Now I just do my chain rule. So the negative 1 comes out, right? Ooh, maybe I should put negative in front here. Negative x. And then it'll be y plus z to what power? Negative 2, because you differentiated, right? Times, now you take derivative of what's in here with respect to y, so that is 1 plus 0. So just 1 out here, right? That's it. And this is really just negative x over y plus z squared. Okay? Any questions on that one? I'm feeling like the partial with respect to z is going to go very much like that just did, right? Partial with respect to z would be just like this, right? The x would still sit out there, right? And the negative 1 would still come out. We'd still have y plus z to the negative 2. And we'd still have 1, wouldn't we? Okay, so it's the same damn thing. All right. All right, so the gradient vector is the vector made up of this here, right? This here, and this here. Let me go ahead and write that on the side. Well, do I need it? I'll put it right here. So this gradient vector is the vector 1 over y plus z, negative x over y plus z squared, and then negative x over y plus z squared again. All right, let's do part B. Find the directional derivative at the point 4, 1, 1 in the direction of the vector 1, 2, 3. So to find the directional derivative, what I'm going to need to do is dot this vector with the unit vector, right, in that direction. So I have to first check, is that u a unit vector? Is the magnitude of this 1? No. How do you check? You take the square root of each of these squared, add up. That's not a unit vector, right? I'll just check it real quick. We'll need the length anyway, right? Square root of that squared plus that squared plus that squared. Root 14. That's obviously not 1, right? So in order to find a unit vector that's going to work here for the directional derivative, I need to take my original vector and scale it by this much, right? 1 over this. So let's use the vector v instead of u. It'll be the vector 1 over root 14, 2 over root 14, 3 over root 14. That is a vector that is pointed in the same direction as this one, but now that one guaranteed has a length of 1. And so to find the directional derivative, I just have to dot this vector with what? With this, but I can't do it yet because this has x, y's, and z's. What do I have to do? Plug in my point, right? My point, my x, y, and z here into that, and that'll give me a vector with numbers in it. I dot that with this vector, and then I'll be done. So let me write it this way. The gradient vector at the point 4, 1, 1 is equal to, let's see, 1 over, we're plugging in 1 for y and z, so that's 1/2. And then here, negative x, x is 4. And then over, oh, that's 4 again, isn't it? Because this is 1 plus 1, 2 squared. That'll turn out to be -1, and then here will be -1 as well, right? Okay, so that is 1/2, 1, -1, -1. So this is the gradient vector. That's the gradient vector at that point. And here's the direction. I dot the 2, right? And that will be my directional derivative. So the directional derivative in the direction of v is 1/2, -1, -1, dotted with 1/√14, 2/√14, 3/√14. And that's just going to be a number, isn't it? Because the dot product always gives you a number. I'm not going to get the number like as a decimal. I'm just going to do it as an exact form. So when I do this and this. Right? 1/2√14. And then I'm going to do plus this times that. So when I add that, it's minus 2/√14. And then another one, right? But minus 3 this time. And yes, you could get a common denominator, put that all together, but whatever, that's an answer, right? Okay. It should be negative. All right, so that just shows you that if your function is a function of 3 variables, we can still define the gradient vector, we can still find a directional derivative. It's just a little harder for us to understand it, like what's actually happening there. The temperature example is just hopefully a way that it helps make a little sense to you. All right, now, maximizing the directional derivative. So what we've done so far, right, is we've just said, hey, look, if you give me a surface, a point, and a direction, I can tell you the slope. Or if you give me this like hypersurface, this thing that I can't really see, right, it's in 4-dimensional space, and give me a point, I can still go point in a direction and go in that direction. I can tell you what the rate of change is in that direction. I can do that. But can we maximize the directional derivative? Can we find a way to find the largest directional derivative, like which way to point to go max, right? The key to maximizing it is to remember this formula when we were studying dot products. Remember that formula? U dot v, the dot product of 2 vectors, is always equal to the magnitude of the first vector times the magnitude of the second vector times cosine of the angle between the 2 vectors, right? That's the generic dot product formula. I didn't prove it, I told you to just accept it, but we're going to use it. So now, if the directional derivative in the direction of u is the gradient of the function dotted with the ab, right? Right? Isn't that what it is? That's the definition of the directional derivative in the direction of u. You know what? Let me put u here instead. Dotted with u. And remember, u here could be a 2-dimensional vector, or u could be what? 3-dimensional, or 4-dimensional, or 5-dimensional, or 6. But this is the u is a unit vector that points in the direction we want to go, right? But by definition of this is the same as the magnitude of this, right? Times the magnitude of this times cosine of the angle between these two, right? Right? So the directional derivative in the direction of u is the magnitude of that vector times the magnitude of this vector times cosine of the angle between those 2 vectors. What can you tell me about this? That's 1, right? Because it's a unit vector. So the directional derivative is always just the magnitude of the gradient vector, right? The magnitude of the gradient vector times cosine of the angle between the 2 vectors, right? And the question is, what would make this directional derivative the biggest it could ever be? When cosine is what? 1. And what angle is going to give you 1? At what angle is cosine 1? At 0, right? At 0. Which means the angle between what? These two vectors needs to be 0, which means the direction you should point in should be the same direction as the gradient vector, which means the gradient vector is the direction you should point in. What? That's weird, right? We're saying, look, if you give me a scalar function, I can calculate this thing called the gradient vector. Then I can calculate, then you give me a direction to point in, right? And then I will be able to calculate the rate of change in that direction. And now I'm asking, okay, what we're seeing here is that if the angle between those two is 0, that's going to be where we get the biggest directional derivative, which means I just need to calculate the gradient vector. And that gradient vector will tell me the direction I need to point in. It's weird. It's weird, right? Is that weird? Does that seem too easy? The gradient vector tells you the direction you should point in. And it's that simple. So let me do an example, all right? Let's do an example. Yeah, let me see. I think I have an example. This in my notes is just me explaining the same thing. All right, so we have here a function of two variables, right? This is a function of two variables. So we're talking about a surface, right? We're talking about a surface here. And that's not the same problem we did a second ago, is it? No, it's not. Okay. So we got this surface here, right? And what I want us to find is, first of all, the direction as an angle of the maximum rate of change at the point 0, 0. So imagine this surface, whatever it looks like, right? Sitting here. Here's my, let's say this is my x, y, z, like this. There's my surface. What I'm saying is go to the point 0, 0 on the ground, right? That's 0, 0. There is some point up here on the surface somewhere, right? So I'm sitting here, got my surface floating above here. I go to 0, 0. I'm up here standing on the surface, right? I'm sitting here. I want us to find the direction as an angle that I need to point in for the maximum rate of change, right? The maximum rate of change in that direction. What direction is it, right? Well, we just said the direction must be the gradient vector, right? The gradient vector, the direction of the gradient vector gives you that direction you should point in. So for part A, what I'm going to do is first I'm going to calculate what the gradient of this function is. And that's going to be a vector. And since we've done a few of these, I'm going to actually do it like I'm trying to just do it, write the vector as I go. The gradient of the vector would be the partial of this with respect to x first, right?